this first question as asking us what is the probability that our actual value is less than a 70. A lot of, or maybe not a lot, but a few people had, I think, a pretty good way of dealing with this. Kiana, what did you do here for this? Yeah, absolutely. So converting that 70 into a z-score. What's our formula for z-score? X minus mu over standard deviation, which works out to be 70 minus 80 over 6.8, which if we do that, so that's negative 10 divided by 6.8, we get a z-score of negative 1.47. Nope, that is the z-score. So that's the standardized, what this 70 represents. In fact, how would we interpret the z-score? What is the negative 1.47 telling us, basically? No, it's an interpreter. What is the z-score? Z-score is a measure of position, not a probability. Yeah, it's the number of standard deviations away from the mean we are. In this case, the fact that it's negative tells us what? Below the mean, which makes sense, right? 70 versus 80. 70 is below the mean, and we're saying it's a little bit less than a standard deviation and a half away from the mean, right? Which should hopefully make sense, right? One standard deviation is 6.8. Half of a standard deviation would be 3.4. 6.8 plus 3.4 would be like, what, 10.2? And we are 10 below the mean rather than 10.2 below the mean. Makes sense. Sure. And so really what this is asking is equivalent to the probability that z is less than negative 1.47. Okay, so how do I then figure out the probability that z is less than negative 1.47? What is the function in my calculator that we are going to use? Well, that will just be the, yeah, normal CDF, right? Normal CDF. In this case, if we want everything to the left, lower than 70, we need our negative bound. What is the lowest z-score possible that we could see here? Is there a lowest z-score? Negative a billion is fine. Negative 10 does the job for us for if we're framing this in terms of z-scores, but technically there is no lower bound, however you want to communicate that. Negative 10 for our standardized value is good enough. We said that the z-score we want to go to is negative 1.47. What is our standardized mean? Standardized mean. 0, and then the standardized standard deviation is 1. Yeah, very good. Which gives us an area of about 0.07078. So we'll call that probability equal to 0.0708. Okay, so that's great. That's fine. That's like a culmination of what we learned in 5.4, kind of mixing it in with what we did at the end of chapter 3 of converting from an x value to a z-score, which is why I said the ability to find z-scores is fairly important for this. That is, of course, though, not the only way to do this. We don't actually have to go through the standardization process for this task. We can. And when we do, this is exactly what it looks like. But we're not restricted in only using that standardized mean of 0 and that standardized standard deviation of 1. What else could I have entered here into my normal CDF if I didn't want to standardize everything? Well, in this case, our lower bound, negative 10 can still work, and I think in this instance would still work. I'm a little bit hesitant to use negative 10, though, just because that was supposed to be like a z-score value. That's a standardized value. Let's maybe do like negative a billion. Just some large negative number. Yeah. Yeah, upper bound. Yep. So you're not supposed to put 70 for upper bound? Well, we're talking about that right now. What is our unstandardized, unadjusted upper bound? If we don't want to frame this in terms of z-scores, what is the largest test score that we could see that would fit the bill here? For A? 70. Now, I don't want to do 69. I don't want to drop it down. I don't want to do 69.9 because when you do that, you exclude all the infinite number of values that exist between our value that we're saying and that upper limit. You want to go right up until that value that we're stating here. So right up to that 70. What is the unstandardized mean? So non-adjusted. 80. And then what is the unadjusted non-standardized standard deviation? 6.8. And we hit enter and we get, okay, it's a little bit different because I rounded this negative 1.47, but it is effectively the exact same answer. In fact, this one's even better because it's not rounded. Okay. So we have the ability to do this through our z-scores, to standardize things, to enter in the z-score values, to use mu as 0, standard deviation as 1. That's totally fine. But because we're doing this in a calculator rather than a table where we would need to standardize things, we can just alter what the mu is and what the standard deviation is in our calculator, and that's totally fine. So for instance, if I wanted to solve B, figuring out the likelihood of scoring between a 75 and an 85, I could convert both of those into z-scores. But I do not have to. What could I instead do? What would I enter into my normal CDF in order to figure out in an unstandardized way the likelihood of falling between 75 and 85? What would my lower bound be? 75. What would my upper bound be? What's my unadjusted mean and my standard deviation? And we get apparently about 53.78% of the data falls between those two values. Which is, again, not different at all. If you did the z-score approach, you should have gotten the exact same thing. If you rounded a little bit early, if you rounded a little bit prematurely, it might be off by a couple tenths of a percentage, but should be pretty dang close. Okay. And for C, if I wanted to figure out the minimum score that a student would need in order to get into the top 10%, what is that top 10% telling me? What is that piece of information there? So scored higher than 90% of people. In other words, we're looking at an area to the right of a particular value, where this area here should make up, what, 10% of my total area? And absolutely right, as Abhi said, that we should have 90% on the left. Cool. How do we do this in our calculator? How do we figure out what this is going to be? How would we get a z-score out of this? Your calculator does it better than mine if you're using the colored version. But we're looking at 10% to the right of a particular value, and that's an area. So we do our inverse norm here. In this case, the area we're looking at is 0.1. We want it to the right. And if we used our 0 and our 1, our standardized values, that would give us the z-score that corresponds to this. But we don't need to use our standardized values. What should I use if I just want to get straight away without needing to run through z-scores? What would I do to get the test score value for this? What would my mean be? 80, and my sigma would be 6.8. And so in order to score in the top 10%, this tells me that I would need to score an 88.71. Area, if you want to do to the left, would be 0.9, but you can also adjust and tell it that you want to do to the right and use 0.1. So 0.1 to the right or 0.9 to the left. Either way, should give you the same answer. I would need to do 0.9 to the left just because that's what my calculator defaults to. So I would have to do, where's my inverse norm? I would have to do 0.9 with exactly the same thing, right?
And then do you have, just for the mean and the standard deviation, do I just do that 0 and 1?
If you want the z-score, then yes. But if you want the test value that corresponds to, then you would need to plug in the mean and the standard deviation that we see here. You tell me.
Okay,
yeah.
Oh, it's the same problem.
Yeah, same problem.
It's just a B.
Yep.
It's 80.
Questions with our bell here? Does this feel comfortable, what we just did? You have questions about where I got any of these values from, what we're doing here? Yeah, Wesley. So B was we were looking between two different values. You could convert those to z-scores. It's probably easier to just do what we're doing here, normal CDF, where the lower bound is 75, upper bound is 85, mu is that 80, and that sigma is that 6.8. Yeah, so it's the exact same normal CDF, but you're giving it like an upper and a lower bound, which in this case corresponds to the fact that the smallest test value we want to see is a 75, and the largest that we want to see is an 85. Any other questions? Well, the good news is this is literally just 5.6. What we have just done is all of 5.6. Ta-da. 6 examples here, but the process is exactly the same, right? We have this ability to go through z-scores if we want to. We do not need to do that. If we were using a table, we would need to do that. But because we're not using a table, we can just enter in the data as is into our calculators, and it'll handle the rest. So I want you guys to take a moment to try this out with what we have here. I'm on, so 5.6, looking at the second page, there's like this beef jerky example. And take a moment to figure out what each of these are. So exact same process, exact same idea. You can calculate z-scores if you really want to. You do not need to. You do not need to go through z-scores. In order to do this, it is the exact same as above.
Just in that case.
So remember, you're only going to use the 0 and the 1 if it's already standardized. So if you're not getting the z-score, then don't use 0 and 1, use the mean standard deviation.
Yeah, I'm already.
Okay, so this is totally fine. You definitely need to calculate the z-score, and then you need to use 0 and 1. But if you don't want to calculate the z-score, you can also use it. Yes.
The first one?
Yep.
If I don't want to calculate the z-score,
Yep.
what would I use for my lower?
You just need it to be small enough that you're not understanding issues. So we were using 10 for the 10 standard deviations to the left. You could figure out what 10 standard deviations to the left is. Why do that though? Just do like -10.
Okay. Thank you.
Yeah.
Oh man, I got one.
That looks good. And I think it's 50. Oh, you're doing area to the left? Yeah. Cool. Cool. That totally works. How did you do this one here?
Oh wait, I didn't put it in again. I gotta do it.
Okay.
Yeah. You're the right thing that I used. I did it again.
You might have done like 2.5 as a standard deviation or something like that. For the first time?
Yeah. I think it's.
Yeah, no, that was good.
Yeah, so that thing right there.
It's fairly small, so if we think about this as like the number of standard deviations. So when, by the time we're at 4, we're almost 3 full standard deviations away, which is actually pretty useful. Like if we think about like within 3 standard deviations, we should have like 1% of our data. You don't have that much when you get that far away. And so it ends up being.
Still gonna do it.
Yes. Yeah, my pen wasn't working for first period, so we did have to go with this. Or I guess that was you guys, wasn't it? Yeah, that was during both. Okay.
Her name is like that. I mean, everyone has a.
All right, let's take a look at what we got here for our first example. So finding the percentage chance that a piece of jerky is less than 4 inches long. So the probability that our value is less than 4. Did anyone calculate the z-score that goes alongside this? You don't have to do the z-score, but did anyone do it? Negative 2.56. Okay, which is fine. If you want to use the standardized mu of 0 and the standardized standard deviation of 1, then calculating the z-score is fine. My only piece of advice here would be to not round this until the very, very end. So like, yes, I'm writing it as negative 2.56. You would want to leave it in your calculator as whatever it is in the calculator and only round at the very end. Yeah.
Good question. So I get the formula for d squared is x minus e divided by standard deviation.
Yes.
I just want to know, like I know they give the mean and the standard deviation, but how do you find that? What's that?
X in this case would be 4.
Okay.
Because that's like the limiting z-score that we have in this case, or the limiting value that we have in this case. Yep. Okay, so this is totally fine. You could run either way, and you should get about the exact same thing. You just need to be careful about rounding here. So, looking at this, we want our, what's a good lower bound here if we're doing our z-score value? What's my standard lower bound going to be for z-scores? -10 is going to be good enough. Z-score itself was, we said, -2.56. Standardized, so 0 and 1 for mu and sigma. We get 0.0052 for our probability. If I wanted to do that without standardizing everything, though, definitely can. In this case, the lower bound, I'm just going to add some zeros just to make sure that, in fact, I am going far enough to the left. In this case, what is the largest value, the largest kind of length that we are seeing here? 4. What is our mu? It's like 4.64. And then standard deviation 0.25. And we get actually exactly the exact same thing. That's nice. So -2.56 must have been an exact value then. But we get exact same thing when we don't standardize it as well. And either way is perfectly acceptable. So this probability is equal to 0.0052. Or 0.52%. And either way, of course, is perfectly acceptable. Okay, finding the probability that our beef jerky is however long. Again, you could convert to z-scores. Of course, you do not have to. That is just giving us a lower bound and an upper bound. So in that case, our lower bound is 4.4. Yeah, upper bound is 4.8. Yep. 0.57. Yeah, 57.04%.
Can I just write what I would put in the calculator? And just write normal. Yeah.
Sure, that's fine.
Actually,
And then finding the kind of minimum length to make us in the top 15%. You guys can set that. If we're looking at the top 15%, then what do we want to be? Do we want to be looking at an area to the right or to the left of this value? Area to the right. My calculator can't do that. You guys can just set your calculator to be the to the right, and that's totally fine. But if it's a length that is 15%, or that is kind of representing the top 15%, then what is the area to the left going to look like? The bottom 85%. And so I can just do my inverse norm. And we'll do the bottom 85%. Whoop. To the bottom 85% with our 4.64 and our 0.25. And I get 4.90-ish as my length. Of course, I would recommend just setting it to be to the right. But this x value is equal to 4.90, which is, again, not a z-score. This is the actual x value, right? This is not the standardized score. This is the actual length. All right, any questions with 5.6? Inverse norm versus the CDF. So inverse norm takes an area and converts it into some kind of position. So either that'll be giving us a z value if it's standardized or an x value if it's unstandardized. And then normal CDF takes position, so either the unstandardized x or the standardized z, and spits out an area. So it just depends on, do you want an area or do you want an x or a z square?
So the problem on top of this one, I tried to do
Yeah.
on top.
Yeah.
For the third part,
Yeah.
you just use
You just use normal CDF for all of these. Yeah. Yeah. The reason why I chose the beef jerky one is because if you look through, I think this is the only one that requires you to use inverse norm, but this is how you would do it. Yeah. Okay. We're going to do something here. Okay. Good question. Any other questions on 5.6 before we move on? If you don't use the z-score, you just have to change the mean and the standard deviation to be what it's there. Lower bound, I just do -1 with a bunch of zeros afterwards, -10 billion or whatever. Whatever floats your boat. But realistically, this is very much overkill. Like if you look at what I've done here, that's very, very much overkill. I'm just doing that because it doesn't take me very long, and it definitely would be at least 10 standard deviations to the left, right? You could calculate what 10 standard deviations to the left would be and then just use that, and that's totally fine. But I'm just going to put in -100 billion or whatever, -10 trillion, whatever this is, and that will be good enough. Unless I'm giving you numbers that are that large in terms of like mean and standard deviation, which like I'm not going to do. Any other questions? Okay. So, nope. This is something else.
basketball.
Okay, so most of Unit 5, kind of the latter half of Unit 5 that we've been working with, has all been dealing with the normal distribution. And apparently this distribution is so important that we are even tempted to standardize all of the values, talking about like z-scores, and we have this entire table that's like dedicated to figuring out those standard values, and it's very, very well analyzed. We can convert like standardized values into areas. It's a very, very thoroughly studied distribution, but like it's surely this is a fairly rare distribution, right? Like it's perfectly symmetrical. It is like we're not going to see skew or anything on it. It has not only being perfectly symmetrical, has these like exact kind of proportions that we see. And so then the question is like, how common are these normal distributions that we would actually want to like learn all of this stuff kind of about normal distributions? That's what we are going to find out with what is called the central limit theorem, which we are not going to discuss at like any level of depth at all. We're just going to kind of discuss kind of the consequences of the central limit theorem and what it means for us in terms of a normal distribution. If you are interested in other aspects of like why does this process lead to a normal distribution, I'm going to upload there's a YouTube video from a YouTuber that does a really, really good job of kind of breaking down kind of upper level math ideas into very digestible steps. that I will post to Schoology if you are interested. It's by no means required, purely if you are looking at this and like, this feels like a very bizarre thing to be true. Why must it be true? So what I have here is called a Galton board, very generously donated by Dr. Guffey, who has also been doing his own kind of like personal study with statistics, and he just had this and was like, oh, I thought it was just like a desk toy, and in fact it is not. It is perfect for the lesson that we are looking at today. And the main idea that we are trying to capture is if I were to drop a single one of these little kind of marble things down, it might be fairly difficult to predict where exactly it would end up. Right? We could probably construct a PDF to figure out what is the actual probability of it landing in a particular bucket. But that would not necessarily be something that would be very, very easy, particularly for something that's very, very complicated like this. Certainly not something that would be necessarily all that approachable. But we could imagine kind of doing something similar to that, and that it would be very, very difficult to predict with a whole lot of accuracy what is going to happen with that particular marble. The central limit theorem, the kind of main tenet of the central limit theorem, is even if a single event is difficult to predict, we can still make generalized assumptions about what a whole bunch of events are going to be doing, about how a whole bunch of events are going to perform. And what is incredibly cool about what we are going to be doing here is that when we are taking a bunch of samples, it doesn't matter what the starting distribution looks like. The final result of our sample distribution will always be normal if we do it well enough, if we take a large enough sample. All right, so here we have our kind of our setup, and what we see when we allow everything to run is not exactly a normal distribution, but something that is remarkably, remarkably close to a normal distribution. And the idea is if we were to, say, increase the number of rows of pegs or to increase the number of marbles that we were dropping, we would get closer and closer and closer and closer and closer to that normal distribution. And you can run this as many times as you like, and there are certainly enough in here that every single time you do this, you are going to get something that at the very least resembles a normal distribution, which is an incredibly, incredibly powerful, really like fundamentally important result in statistics, that you can just do this as many times as you like, and you are always going to end up with something that looks like a normal distribution, which is just absolutely insane. And we could imagine, yes, we could do this if the marbles themselves had a normal distribution, if there was a normal PDF for each individual marble. But you could also do this if it was skewed. You could do this if it was kind of bimodal. You could do this with any distribution that you like, and the result is always going to be, for a large enough value of n, something that approximates normality. Now, what large enough means for us, I know in AP Stat, the large enough was like 30 is big enough. There's something called a t-score, which is like what happens if n isn't big enough for me to be confident that what I'm looking at is normal. And what you see is that t-scores and z-scores end up being very, very close together when they're like around 30 data points. And they get even closer together right around 100. So there's like a limit to where you can start saying, okay, at what point can I stop using t-scores and start using z-scores? And it'll depend on what class you're in. And we'll get into that maybe towards the end of this course. But I just want the key idea here to be the very simple one of we are taking a sample from an original distribution, and it doesn't matter what that distribution looks like, the distribution of the samples is going to be normal if we take enough samples, which is cool. All right. Okay. Couple of things that I do want to note here. We do have a little bit of conflicting terminology with what we are talking about. Very specifically for this distribution that we are talking about, again, I want to emphasize this. This is separate from the PDF that we are going to be given right up front. This is a PDF that we are generating by taking a bunch of samples, by essentially running a simulation with the PDF that we are given up front, which means it's not necessarily going to have the same mu. It's not necessarily going to have the same standard deviation. Okay, I lied. It is going to have the same mu. We have to adjust the standard deviation, though. It's actually mathematically not going to work out to be exactly the same standard deviation. So when we're talking about the mean of our sample means, which is the terminology, the fun linguistic bit of statistics that is fantastic, I am going to label this as mu sub x bar, which is just to say my mean that I get from my sample.
Yeah, got it.
This is the same as just our normal population mean. All right, so we don't have to make any kind of adjustment on our expected value. Expected value stays the same. Standard deviation does not stay the same, though. So our standard deviation for our sample mean, which I'm denoting as sigma sub x bar, is equal to what is called the standard error, which is fairly straightforward how we find standard error. This is just going to be the original sigma, but we're going to divide it by the square root of n, where n is the sample size that we are taking, right? So n, in the case of my Galton board, would be the number of marbles that I'm dropping through in order to get my distribution. This also gives us a slightly adjusted way to find the z-score for a sample mean. All right. So if we're thinking of a z-score for our sample, well, this is going to be that sample mean that we calculated minus the mean of the sample means. Welcome to the linguistic element of statistics, divided by the standard deviation of the sample means. But okay, we know that the mean of the sample means is just the mean, right? That hasn't changed. So this should just be our value here minus the mean. Okay, but the standard deviation actually does change. This is standard deviation divided by the square root of n. Okay, so this does a couple of things for us. First of all, this just allows us to treat large enough samples like a normal distribution, but maybe the original distribution that we're pulling from is already a normal distribution. What then does this kind of sampling modification do? And to that end, I'd like us to just briefly consider. If I randomly select a student and their performance on a quiz, and I tell you that that student got a 75 on the quiz, versus if I took 15 people in this room and told you that the average of those 15 people was a 75. Which one would you be more confident in as a predictor of your success? The one random person or the average of my sample of 15?
Average of the sample.
You'd expect the average of the sample of 15 to have a lower variance. You would expect it to be able to more accurately predict the actual kind of true results that we are getting here. And that is why we are taking the original standard deviation and we are reducing it by this factor, which just says the more people we sample, the less variance we would expect to see. Right? If I'm sampling 100 people and I tell you that their result is a 75, that should give you even more confidence than if I were to tell you that 10 people got a 75, or the average of 10 people was a 75. Confidence, of course, meaning not necessarily on how you're going to perform on this quiz, but confidence that that is in fact close to what you would expect to see on the quiz, right? That there is low variance. All right, questions with our sampling definitions here by our central limit theorem. Okay, the good news for us is that this is going to be the exact same thing that we did in 5.6, except we just need to slightly modify the sigma. We just have to divide by the square root of n. And that's it. And otherwise it is exactly the same. So for instance, taking a look at our first example, we're told that a study has shown that children under the age of 10 watch an average of 25 hours of television a week. We are assuming that the variable is normally distributed, that the standard deviation for that particular PDF is 3 hours. We are then taking a sample of 20 children who fit this demographic and looking for the probability that the sample mean is greater than 26.3 hours. Okay. So we need to go through, we need to figure out our mean that corresponds to the sample. The mean that corresponds to our sample, as well as the standard deviation that corresponds to our sample here. So what is the mean that corresponds to our sample?
25.
Yeah, it's just 25. It's the exact same thing as the mean, which in this case is 25. What is the standard deviation that corresponds to this sample? It is not just 3.
It's,
It's a 20.
It incorporates the 20. So what is it going to look like?
29.
Not 25 minus 3.
25C3.
Not 25C3. No.
20 times 3.
No, not 26.3. What's our...
Oh,
Ah.
Well, it's 20.
So it's
I think it's 20.
3 divided by.
Let me think.
3 divided by the square root.
3 divided by the square root of what? Of 20, which represents the size of our sample. So this is sigma divided by the square root of n, which is equal to 3 divided by the square root of 20.
But good question. So why is it 3 divided by square root of 20, and why is it not 20 divided by square root of 3?
You're more than welcome to watch the 3 blue 1 brown video that takes a look at why all of this is what it is. Because he goes into much more thorough depth than what I am capable of going into.
So what video do you have to watch again?
I'll upload a video to Schoology that does a very good job of covering why all of this works out to be what it is. There's also a Khan Academy video talking about the central limit theorem as well. That would also be a good resource. But you just need to remember sigma divided by square root of n. But the short answer is it's because we're taking the standard deviation and we're trying to reduce it by a factor. And the factor that we are reducing it by is the square root of n, which is the exact same thing that we see there. Okay, so we have our mu, we have our standard deviation, and we are trying to figure out we want to be to the right of this particular value. Right, because we're looking for that mean to be greater than this particular value. So we're going to our normal CDF. In this case, if we're looking to the right, what is the lower bound? What is the lowest average number of hours that we would like to see? $26.3. Okay. Is there an upper bound? No, I'll put in like 1 million, 10 million, whatever that is. Okay. What is our mu for our sample? And what is the standard deviation for our sample? 3 over the square root of 20, which gives us about a 2.63% chance of seeing an average like this. So fairly unlikely. We would expect this to be a pretty improbable result.
To have greater than
To see an average from a sample of 20 that is
greater
than 26.3. Yeah, that's a pretty unlikely result. What if we had only sampled one person rather than sampling 20 people? What if this was literally just, hey, we have a normal distribution. I want to know the likelihood that one person that we pick has this particular value. Well, what would our n be in that case? N would just be 1. Divided by the square root of 1 doesn't do anything, right? So we could go through this whole process again where we want to know the likelihood of having just a single person who fits this criteria. And what we find is that the likelihood of one person seeing 26.3 or more hours is about 33%. Okay, it's about a 33% chance. Which is a lot more likely than a 2.67% chance. But again, if we're trying to say that the average, if we take a group of 20, is this much higher than the mean, that should be a lot harder than having a single marble that ends up somewhere in the outskirts of Nowhereville, right? It would be very, very weird if I turned my Galton board upside down and all of the marbles ended up over here versus having a single marble end up over there, right? And so the idea here, the larger the number of samples, the harder it is to get these really, really rare kind of extreme results.
For the 3 over square root of 20.
Yeah.
If you just put that in the calculator, it gives you like 0.67. Can you put that in instead of the whole entire like 3 over?
You can. I would just be careful not to round. So the reason why I'm putting in this exact value is to make sure that it's like the exact value. Yeah, so I'm not rounding. Yeah, just be careful about rounding prematurely. That's the only thing. Any questions? All right, take a stab at the one underneath. Figuring out if we are taking a random sample of 36 computers, the probability that the average computer age is between 90 to
Okay.
looks good. I would, it rounds up to 0, right? I would include that 0 just to show that you went to the 4 decimals and then it rounded up. Or no, like I would do like 0.9210 just to show that it rounded up to the 9210. Right? Because like this is what's rounding up. It's rounding up. It's fine either way. Like generally speaking, it's going to be 4 decimals. And so that's what you want. Like it's technically equivalent, but it just shows, hey, I measured to 4 decimals, and this is what I got with that method. Okay. Yeah, that looks great. Yeah. I think I know something. Should be right.
Oh, because you didn't do it.
Oh, I see. Oh, I don't have two. Second. Normal.
Yeah.
Lower is
100.
upper is.
Oh, did you do
Divided by square root.
And 6.
This is. Was it?
There you go.
I don't know. 6, and this is 2.66.
You get the 2.66 by doing
But,
Oh, you have to put in,
Yeah.
0,
Yeah.
9, and then 6.
Louis. Good enough.
What? 96.
Okay, so let's take a look at what we have here. What is our mean of sample means going to be? What mu should we use?
96.
96, all right. What does our sigma of sample means look like?
2.6.
Okay, so you can plug that in as into your calculator. Goodness, not even keeping track of what I want to write. 16 divided by the square root of 36? 2.6? It's like 2.67?
Yes, 2.6 would be it.
Okay. And again, just be careful about rounding. Perfect. And we want to be between 2 values. So this would be our normal CDF. Thank you, Lana. Normal CDF. What would our lower bound be? 90, upper bounds. And then we said the mean was 96 and the standard deviation 16 over the square root of 36. And we get 92.1% of the data, or I would put it as the probability of landing between these two, 0.921. We could convert it into a z-score. Nothing wrong with that. But also, again, our calculator's doing it for us, so why would we go to the extra lengths of converting it to a z-score? And that's it for Unit 5.
This is gonna be on the.
So this will not be on the quiz. It will be on the test that we have on Thursday, but not the quiz we have tomorrow. So speaking of this, we have a 5-4-5-5 quiz tomorrow. That's just over the, like, if I give you a z-score, what's the area? If I give you an area, what's the z-score kind of stuff. And then a little bit about, like, if I give you an x value, what's the z-score? If I give you a z-score, what's the x value? So, like, converting between those two. We've got about 20 minutes left. Do you guys have any questions from either the practice that we did on Friday or from the Pearson that you would like to go over prior to the quiz that we have tomorrow?
So what would the quiz be about?
Quiz is over 5-4, 5-5.
I don't know anything. I'm a teacher, so I don't know. That's true. That's true. No support else in the
Exactly.
Yes.
Which is like drops so drastic.
Just one, nothing.
Then as soon as it like changed before to 2007, it was like,
Exactly. That's true. Exactly, you can. Exactly, you can.
Yeah, so like,
Why do you say it like that? So matter of
I'm
fact.
sorry, what did you say?
Did I
Is there due tomorrow?
those are due
No, bro. I'm good. No, I'm good. Yeah, you did.
we used to
No, you did.
0.9, right?
That's fine.
Using on this nice and this answer.
Was it two evils, but.
But it's not
36. Square root of 36. 36.
No, I know.
No, yeah.
Which gives you.
No, you're good.
My zeros just set, that's it. My zeros just
It's
same.
a skill issue.
My handwriting.
It's a skill issue. You should work on
The handwriting diff.
I know all my teachers are
it. Did you get this? Is that because of the stroke?